Hello and welcome back to this discussion on privacy in machine learning in general and in general for statistical notion of privacy that we have been looking at. So, just to recap what we have looked at so far, we looked at a very simple idea of ensuring statistical privacy, which was as follows. Just a quick recap: we have a bunch of variables x1 to xn. In this case, we thought of these as binary variables where each xi was in 0 and 1, and our goal was to compute the average of these xi's. The example that we looked at was, you are trying to do a survey and you want to know the average number of people or fraction of people who voted in a locality. That was the running example we were looking at. And we looked at this technique called randomized response, which will not output x's. Instead of x's, it will output y1 to yn, where y1 to yn are random variables, where yi equals xi with some probability. In our case, it was e to the epsilon by 1 plus e to the epsilon, and equals 1 minus xi with the remaining probability, which is 1 by 1 plus e to the epsilon. That is, you flip the your outcome with a certain probability which is less than 50%, depending on what our epsilon is, that probability will be determined, and you report the truth with more than 50% probability. So, that was the randomized response mechanism, and we argued that there is a certain notion of privacy that this mechanism guarantees, and that is, if you have two neighboring kind of data sets x and x prime. When I say neighboring data sets, so everything in x and x prime are the same except one entry. Then so if you fix any bit pattern b, right, so which is a bit pattern in n dimension, that is something that you are observing, doesn't matter what you observe, no matter what you observe, and that's the important thing. So, you fix any bit pattern b, the probability that the randomized response mechanism on x generated this bit pattern divided by the probability that the randomized response mechanism on x prime generated the same bit pattern is less than or equal to e to the epsilon, right. So, for all b, right. So, for any b, any bit pattern, that is, no matter what I observe as output. Now, I observe something as output and I ask the question whether did x generate this output or x prime generated this output. Because it is a random mechanism that is generating the output, I have to talk about probabilities, and the probability that x generated this output that I am observing divided by the probability that x prime generated this output is not too far away, right. So, that is bounded by e to the epsilon. Now, epsilon is a quantity that I can as a privacy as a privacy enabler, right. So, I can fix this epsilon and we can agree on how much privacy we need, and smaller the epsilon, the better is the privacy. On the other hand, we also looked at what is the utility of this randomized response mechanism. So, this is the privacy part of the mechanism, and we looked at the utility, we looked at a utility question, and we asked the same question. We asked for the same response mechanism, we asked the question, well, if I observed a bit pattern and I did something with it, and then I computed an estimate for the average which I really want to estimate, right. So, the average of x1 to xn, then how close in some sense can I get to the average, right. And for that we said that, well, you have x1 to xn, which is the ground truth which you do not observe. Instead, you observe y1 to yn, which is a random version of this, and now you do some debiasing, which we saw last time, to get z1 to zn, and that is because the expected value of y's is not exactly x. So, you will have to subtract out certain term from y and then scale it by a certain amount to get that expected value of z equals x, zi equals xi for every xi. So, now you have some kind of a good estimate, or at least you hope you have a good estimate for xi via zi, and so now what you are what you can really compute as an estimator for the average of xi's is the average of zi's, right. So, sum over I zi divided by n, and now we asked how good is this in estimating the average of xi's. But remember, because y's are random and z is just some scaling and subtraction from y's, z is also random. So, the average that you are computing after this experiment is also a random variable. So, if you want to ask the question, how good is the average that you compute via z's in estimating the truth, there is nothing random about the truth, the average of the truth. Now, we have to use the language of probability, because what we are estimating is a random quantity, and we said that, well, the chance that with very high probability, WHP with high probability, the deviation of the truth, deviation of what we estimate from the truth, that is the average, the true average minus the estimated average, is at most something like 1 by epsilon square root of n, right. So, it is of this order, right. So, that is and we noted that. So, this is giving us a nice trade off between privacy and utility via this simple parameter epsilon, because the smaller the epsilon, the higher is the privacy, but smaller the epsilon, the larger is the gap from our estimated value and the truth, or the larger is the chance of deviation from the truth. So, if you do not want to deviate too much from the truth, you will have to set a high value for epsilon, but then that means that you are losing out on privacy. So, there is going to be this trade off that we will have to live with, but if you fix an epsilon, from some amount of privacy that we want, and if you also want some amount of deviation with very high probability, then we can kind of figure out what is the number of samples that we would need, because the utility also depends on n, which is the number of samples. So, we can ask the question, how many samples, how many people should I survey, so that if everybody follows the randomized response mechanism using a certain epsilon, so then I will have epsilon privacy, and my estimate is not going to be too much away from the true estimate, right. So, this will also tell me how many people I should survey, because you can work backwards if you fix an epsilon and an utility value to figure out what is the n that you need. In that sense, this is a good way to balance this trade off. Okay, so this is what we saw last time, and then towards the end we said that, well, we can go to a slightly different model, which we noted as the trusted curator model. Let me just remind you what the model was. In this model, you have a curator who is trusted, right. So, in other words, the surveyor, to go back to our previous example, if I am surveying all of you, and you trust me, in the sense that you do not have to randomize your response and give me, because you trust me. But what am I going to do? I am going to compute the average, which means that if you are trusting me and giving me the exact values of whether you voted or not, I will compute the exact average myself. That information I do have, but if I release that to the world, you not necessarily trust the world. There may be an adversary sitting outside who might have access to everybody's information except your information, and now if I release the average to the world, well, the adversary has everybody's information except yours, and also the average of everybody including you. So, it is just a matter of some simple calculation to figure out what your value was, whether it is 0 or 1, right. So, if you know the average and if you know all the values except one value, you can figure out what the missing value is. So, so that is a breach of privacy. So, which means that even though you can trust the curator, you do not trust the world, right. So, now the question is, in this different setup, do we still have to do randomized response, but can I somehow take advantage of the fact that I am actually trusting the curator? And we said that, well, you can actually take advantage of this fact, and the way to do this is, one way to do this is using this notion of differential privacy, which is what we will focus on this lecture, and as I mentioned last time, so this was introduced by Cynthia Dwork, I guess in 2010. Okay. So what is the definition of differential privacy? So, let me put down the definition, and then we will talk about what are the implications of this definition, right. So let us think of some mechanism M which takes in some n values. You can think of these as n binary bit vectors if you want, or this can be some a binary binary digits, right. So, like how in the survey example where everybody is just giving a 0 or 1, or these could be some numbers, this could be anything, right. So, in general there is some space which I am going to call as x, and from that space I am getting n different values, and then there is a mechanism that maps this to some other space y. For example, in the survey example, x is 0 1 n, and then my average is going to be some number between 0 and 1, and that would be my y space, right. So, in general there is some mechanism which maps input to output, and now I consider two what I am going to call as neighboring data sets, and this is the standard terminology for this as well, x and x prime, both belonging to xn, and when I say neighboring, I mean the following. So, that any two data sets that differ in only one single entry, right. So, like how in the survey example you have votes from n different people and just one vote is changed, right, and there it can change only from 0 to 1, but in general you can think of this as you have an instant space x. So, you have n different points from this instant space x, and then I replace one point with some other point in the same instant space x. For example, if your instant space is just the two dimensional, let us say all vectors of length 1. So, then you might have a data set which has these 4 points, and now let us call this x1, x2, x3, x4. So, that might be one data set, and now I might have a fifth point x5. So, now the data sets x1, x2, x3, x4 and x1, x2, x3, x5, right. So, these are both data sets of 4 points, and they are also neighboring data sets because there is just one point which is different from x to x prime. Let us say this is x and this is x prime, right. So, that is a general understanding of what I mean when I say two data sets are neighboring data sets, right. So, let us say we have such two data sets. Now, we will say the mechanism M is epsilon differentially private, right. So, if for all x and x prime neighboring, and all S which is subset of y, and I will talk a bit about what that means, we have the following requirement. The probability that m of x belongs to S divided by the probability that m of x prime belongs to S is at most e to the epsilon. Well, what is this saying? So, this is saying something very similar to the argument that we did for randomized response. It's in some sense you can think of this as a clean way to generalize the the guarantee that we had in randomized response. Not just a clean, a more natural way to do this for any instant space x and any output space y. Basically, we are saying exactly the same thing, right. So, we will call a mechanism which takes a data set and then outputs some value, an epsilon differentially private mechanism, if for every subset S in the output space, the chance that m of x lands in this subset divided by m of x prime lands in this subset is at most e to the epsilon. Now, all this is essentially saying is, if I know, right. So, if I am told that the output of the mechanism M belongs to a certain subset S. Now, I should not really be able to figure out whether the mechanism's input was X or X prime. The same idea. The only thing we are saying here is that we are not just saying, it need not be the case that Y is a discrete space, right? So, Y can be any continuous space, which means that anything that you can measure in the output space in a probabilistic fashion, right? So, any measurable set in the output space, which is why we'll have to worry about any set S in which is a subset of Y. If I just told you that I am observing an output in this subset S, then the chance that the mechanism generated it to, that belongs to this S divided by M of X prime belongs to S is bounded. Now, again, in the randomized response case, we did not have a subset business there because our output space was discrete. We had n bit patterns and the output was also a bit pattern of length n, right. So, and there are only 2 to the n bit patterns of length n, and now we are saying for each of these, right. So, for each one of these bit patterns, the guarantee holds, which means that if you take any subset of bit patterns, right. So, now let us say output space Y in the previous example, what was the output space? The output space Y is just 0, 1 power n, because it is a bit pattern that we got. Now, you can take any S which is a subset of 0, 1 power n, right. So, it is a subset of this output space, which means that let us say it is a bunch of bit patterns. Let us say I have B1, B25, B108, right. So, there are 3 different bit patterns, maybe n is 10, which means that there are a total of 1024 bit patterns, which is 2 to the 10, out of which I care about, I am told that I am observing something which is either B1, B25 or B108. Now, I want the guarantee that the probability that M of X belongs to, let us call this set S, right. So, S divided by probability that M of X prime belongs to S. Now, what is this probability? Because this is a discrete space, I can simply say that this is just the probability that M of X equals B1 plus probability that M of X equals B25 plus probability that M of X equals B108, right. So, it is just a sum of these probabilities. Because why? Because if you observe B1, you cannot observe B25. If you observe B25, you cannot observe B108. You observe only one of these, and then these are mutually exclusive events. So, I can sum these things up, right. So, now I will have the sum of these probabilities, and now I will divide it by probability that M of X prime generates this plus dot dot dot, right. So, those 3 things. Now, what we argued there was for each individual things, right. So, the ratio is bounded by e to the epsilon, and now it is not too hard to show that if that happens for each of this, then the sum of this divided by the sum of x prime will also be bounded by e to the epsilon. So, that is the so we showed it for every individual output in a discrete case, but in a continuous case what happens is if you ask for every individual output value, well, we know that for continuous distributions these are going to be 0, the probabilities are going to be 0. So, this does not really make sense, and that is why this is a more generalized definition which says that you care about every measurable set in the output space, and the same definition should hold, right. So, but the idea is the same, right. So, you are observing something and you should not be able to say whether it came from x or x prime. So, this is what we want, right. So, we have not told how to achieve this, right. So, okay, so I should make a small correction here, that in the previous case y was 0, 1 and not 0, 1, right. So, the mechanism outputs a bit vector and then I worry about the average, but the mechanism itself is just outputting a bit pattern. So, that is a clarification I had to make. Okay, but in general it can be some continuous space, y can be some continuous space. Okay, so now what are we then saying is the following. How do we achieve epsilon differential privacy? That is the question we are asking in the trusted curator model, right. So, remember in the trusted curator model, we are not releasing x1 to xn, we are releasing some function of x1 to xn, maybe it is the average that we are releasing to the world, and now by looking at the whatever I am releasing to the world as the average of x1 to xn, I should not be able to figure out whether the data set x generated this average that I am releasing to you, or the data set x prime generated the average that I am releasing to you, right. So, that is the thing, and to achieve this, Cynthia Dwork, she herself proposed this mechanism called the Laplace mechanism. So, what is the Laplace mechanism? To define the Laplace mechanism, we will first define what is called as sensitivity. Okay, what is sensitivity, right? So, let us say you have function f which goes from xn to r. For our purposes, let us say I am interested in the average, right. So, which is what I am releasing to the world, the mechanism is going to release it, the average to the world, and now I will define my sensitivity as the following. So, I look at the maximum over all x and x prime which are neighboring, how sensitive is this function if I change one input. Basically, that is what I care about, right. So, what I am saying is I look at f of x minus f of x prime, right. So, so this is, remember there is nothing random at here, right. So, this is just a function that I am interested in computing and telling the world, right. So, that is the average function, and I am asking how sensitive is this function itself, which means that if I take any two data sets which are neighboring and I compute the average for both of these data sets, and I am asking how much can they potentially change, right. So, how that's, I mean, by how sensitive is the function itself to one input change, right. So, that is basically what we are asking here, and just to compute this, right. So, this should be very easy to compute, but nevertheless we will do it. So, if you want, you can pause and try this out. So, try to compute the sensitivity of the average function when you have a bit pattern of n dimension, right. So, if you have n bits, what is the how much can the average change, right. So, which means that basically what we are asking is if you have x and x prime which change just in one bit pattern. So, one bit, I am asking xi, I mean the average of xi's minus the average of xi primes, how much is this changing, right. So, that is basically what I am asking, and I know that it is x and x prime, those two data sets change in only one single quantity, right. So, one single bit, whichever bit that is, right. So, this is 1 by n. So, let us say it is the last bit without loss of generality, minus sum over I equals 1 to n xi prime plus xn minus xn prime. Now, because these are neighboring data sets, I know that the first term of these two first terms are the same. So, I can kind of cancel them out. So, this is just 1 over n absolute value of xn minus xn prime, and because these are binary bits, if xn is 1, xn prime is 0, if xn is 0, xn prime is 1. So, the difference has to be 1. So, this is just 1 by n, right. So, the sensitivity of the average itself is, the delta is just 1 over n. So, basically what we are saying is that if I change only one bit of n bits, then the average can change by 1 by n in absolute terms, right. So, that is what that's a definition. I mean, that's a quantity which we are interested in. Now, what is the mechanism, right? So now, knowing that, you know, I want to release the average to you, and I know that for neighboring data sets the average changes by 1 by n. So how can I now construct a mechanism that uses this information to give you something? Well, we will, because our notion of privacy is probabilistic, so my mechanism has to be randomized as well, right? So which means that I need to give you not the average directly, but some, you know, random version of the average. So and the randomness that we are going to introduce is using what is called as the Laplace distribution, and that's why the mechanism that we will come up with, it's a simple mechanism, is called the Laplace mechanism. Okay, so what is the Laplace? How does the Laplace distribution look like? Well, it's like your Gaussian distribution with a slight twist. So the density function of Laplace mechanism at any x looks, well, it looks like 1 by 2b e to the minus x minus mu by b. This looks like my Gaussian distribution. You know, it has a center and it has what is called as a spread parameter. If you recollect your Gaussian density, that's going to be 1 by square root 2 pi sigma e to the minus x minus mu squared by 2 sigma squared. This is of similar form. The Laplace mechanism itself will, you know, the density function itself will look something like this, right? So it is more sharper at your mean. In this case, the mean is mu, and b is a measure of variance. Okay, so so this is the Laplace distribution, and now how do we use this? Well, we use this in a very obvious, in some sense, this very simple way to achieve a mechanism. So the Laplace mechanism is as follows, right? So the Laplace mechanism tells us to do the following. You compute your f of x, whatever your x is, your input data set, you compute your function and then add noise to it, right. So, and this noise is a probabilistic noise, and the noise has the following property. It is not any noise, it comes from a Laplace distribution with mean 0 and the spread parameter given by delta by epsilon, and delta is our sensitivity of the function that we are interested in, sensitivity of f, and epsilon is the privacy parameter that we care about, right. So basically you should think of it as follows. You are adding a zero mean noise, which means that on an average you are still, I mean, in the expected value of the output random value that I am releasing to you is the truth, right. So it's an unbiased estimator that I am outputting to you because it's zero mean, but there is some noise variance or spread associated with the noise that I am adding. And now if you think about it, how much variance should the noise have? Well, that depends on two things, right. So one is the function that you are trying to compute, second is how much privacy you need. The smaller the amount of privacy that you need, which means that or rather the larger the amount of privacy that you need, if you want your privacy to be really high, then you have to add more noise, quantitatively, statistically more noise, right. So which means that if the larger the privacy that you have, that you need, smaller is your epsilon is going to be, because remember, epsilon in our definition being small would mean that I'll find it harder to distinguish between x and x prime. So if epsilon is smaller, then what I am saying is that, you know, if that's a stringent notion of privacy that I need, which means that I need to add more noise, and we'll see why this is needed, and that's what this is at least telling me, right. So because epsilon is in the denominator, the smaller the value of epsilon, the larger is going to be the variance of the noise that I'm adding. The second thing that will determine the mechanism's privacy overall is the sensitivity of the function itself, right. So, if the function is too sensitive, right. So, if I change one value and the function changes by a lot, then I need to add more noise. Again, we will see, we will try to intuitively understand why this is the case, but at least this definition is telling me that, right. So, this mechanism's definition is telling me more the sensitivity of the function, the more the noise that I should add, because this parameter that I am adding here is kind of the variance, right. So, higher the sensitivity, larger the noise, higher the privacy requirements, smaller the epsilon, and hence larger the noise, right. So now what can we say about this mechanism, and that is the mechanism, right. So, that it is as simple as that. So, you compute, in this case, if you want to compute the average, then you would, for average, right. So, because we computed delta for average, so you would compute the average, the curator, the trusted curator will get the data x1 to xn, will compute the average and will add a noise, and that noise is Laplace with 0 mean and 1 by n epsilon. Why is it 1 by n epsilon? Because my delta, we just argued the sensitivity of the average function is 1 over n, right. So, the noise variance that I am going to add is of the order 1 by n epsilon. Basically, I am substituting delta equals 1 by n here, right. So, for this specific function that I would like to release. So, let's try to understand this a little bit more. I mean, it should first of all, you know, let me say that, you know, can argue that the Laplace mechanism is epsilon differentially private. I will just say dp to indicate differential private. That is, if you add noise whose spread parameter or the variance is proportional to delta by epsilon, where delta is the sensitivity of the function that you are trying to release to the world, then this mechanism, simple mechanism of adding noise to whatever you have computed, is in fact epsilon differentially private. That is, you are outputting a random quantity, and that random quantity satisfies our definition of epsilon differential privacy. That is the first good thing about this, right. So, now let's just maybe spend a minute to understand why sensitivity and privacy parameter, how does that relate to the noise itself, right. Now, what is this, what are we saying by this mechanism, right. So, you know, let us say I computed the average of n different things, n different numbers, maybe bit patterns, maybe something, right. So, but then my goal is to release the average to the world, and let us say the average was this particular value, right. So, this is x bar, that is x is some data set, and x bar is just, you know, 1 over n sum over I xi. Maybe they are bit patterns, which means that this is going to be a number between 0 and 1, maybe they are just numbers, in which case it is some number in the real line. Now, if I have a neighboring data set, which is x prime bar, for which I will compute the average, which is x prime bar, x prime I. Now, if it is average, then I know the sensitivity is like 1 over n. Maybe it is a different function, right. So, maybe it is the average, maybe it is a different function. So, now let's first look at the average and then we look at a different function. Maybe for the average, it is going to change by, this is x prime bar. Now, my goal is to not let you figure out whether the output that I am giving you, which I am claiming you is the average of the input that I have, came from the input x or x prime, right. So, because, you know, I am a trusted curator, I want to, you know, ensure the trust of everybody who is giving me their data. I computed, I got my input, and now I am going to corrupt it with noise and give it to you, right. And then you, by looking at the noisy version of, let us say, the average should not be able to figure out if the input on which I actually computed the average is x or x prime. That is the guarantee that we want to achieve, right. So, which means that, you know, if x and x prime, right. So, if the maximum deviation between the average for any neighboring data sets is this much, right. So, let us say these are the maximum, this is the maximum that the average can deviate. Now, what happens is the following, right. So, I am, if it came from x, now I am not going to, I will compute x bar, I would have computed x bar. Let us look at this scenario where the actual input was x, you do not know that yet, right. So, the actual input was x, so I computed x bar and now I am corrupting it with noise, which means that, you know, I am outputting not x bar, but a random quantity which is centered at x bar. Why? Because I am adding some noise to x bar and that noise has 0 mean, so that the mean of the output that I am giving you is in fact x bar, right. So, which means that the density function of what you are actually observing is going to look something like this, right. So, it is going to peak at x bar and then it is going to drop like this, because it is a Laplacian distribution, mind you. Now, well, how much will it peak? Well, that depends on how much noise I am adding, right. So, the noise will determine the spread of this, you know, distribution. Now look at the scenario where this guy, where the input that I got was actually not from x but from x bar, right. So, in which case I would have given you something that was centered at x bar, right. So, this is the statistics, or this is the density function of the random variable that you are observing, right. Now, by looking at the value, right. So, let us say you observed something like this, right. So, you observed this value, or maybe I will take a different example, maybe you observed a value here. Now, this is the only piece of observation that you have, right. So, now you are asking the question whether did I generate this value by adding noise to x bar or x bar prime, that is the question you are asking. If you are able to figure that out, then you know you have broken the privacy. Now, which means that roughly, right. So, I have to look at the density of observing this point if the truth that I had computed was x bar and then I added noise, versus I computed from x prime bar, right. So, now if these two things are much different or very different, right. So, for example, if I had added much lesser noise to the same example, you know, here is another, the same setup, but the amount of noise that I am adding is different, x and x prime bar, it is the same thing, but now I am going to add much lesser noise, right. When I say much lesser noise, the variance of the noise is much lesser, which means that, you know, it is going to fall much faster down to 0. Okay, my diagram is not that well drawn. So, it will never hit 0, but the point I am trying to make is the fall will be much steeper, because, you know, my variance is small. So, I am almost going to see values which are close to x bar. So, if I had added much lesser noise, this is the density of the output that you would see, right. So, but then if I did the same thing, but had I got it from x prime bar, again this would be like this. Now, let us say the truth, I mean you do not know the truth, right. So, but then let us say the truth was x bar, right. So, the data set was x, which means that I am much likely to get something closer to x bar. Now, look at the density difference between this value having come from x or x prime. Now, essentially what I am saying is that if this is what I observe, if orange is my observation and that is what I am claiming is the average, by looking at the orange, now you know that this is the mechanism that I used. Now, you know that it is much more likely that the orange value came from x bar noisy version of x bar than it's a noisy version of x prime bar, right? And that is because I added much smaller amount of noise, whereas here, you know, this difference, no matter where I observe, right? So it doesn't matter which is the one that I observe, but the ratio of this difference is still going to be smaller. Basically, these two guys have to look as close to each other as possible, these two curves, these two densities. And if these two densities have to look as close to each other at all places, then the only way I can achieve is by adding noise that is proportional to how much is the sensitivity of the function that I am computing. If the function is not too sensitive, which means that there is already some amount of stability between x and x bar, right? So the function that I'm giving you is not going to change too much whether it's x or x bar, no matter what the neighboring data set says, which means that I can get away by adding small amounts of noise. On the other hand, if the function is too sensitive, now I have to add more noise to confuse you whether it came from x or x prime. So which means that, you know, the noise that I'm adding has to be proportional to the sensitivity of the function that I'm computing. That's what this picture is telling me, right? So just to make that point clear, I'll draw one more picture. So now instead of x and x bar, instead of computing the average, maybe this was some other f of x, right? So this was f of x, and now this was f of x prime, right? So there are two neighboring data sets where this function, not necessarily the average function, maybe some other function, but then it's too sensitive, right? So if I change one data point, f of x becomes f of x prime. Now I have to add something to f of x, right? So now if I add a noise like this, you know, now let's say if I got it from x, right? So which means that I'm going to observe somewhere around f of x, and for that the density of f of x prime is too small, right? So which means that, you know, I cannot confuse you whether it came from f of x or f of x prime, right? So which means I have to add more noise in this case because the function is too sensitive. I have no other option but to add, you know, more wider noise like this, right? So wider noise like this, so that, you know, this gap, this ratio is still bounded. Well, what should it be bounded by? Well, that is the amount of privacy that I am essentially guaranteeing, right? Well, it's not exactly this ratio, but yeah, so you can, this ratio will play an important role, right? So because you are talking about probabilities, and that probability is going to come from, you know, these densities, integrating these densities. But how much is this gap that I will agree as a reasonable privacy is the epsilon parameter, right? So maybe in this case, well, if I don't care about so much privacy, well, then the first part itself is okay, right? So maybe this is okay, right? So maybe I am okay with this amount of difference between this amount of distinguishability between f of x and f of x prime. Maybe that's what my privacy requirement is, in which case I can get away with, you know, lesser amount of noise. But if I have a stringent notion of privacy, then that's also going to dictate, you know, what this ratio that I am tolerating in some sense, right? So ratio of the densities, and that will also mean that I should add more noise if I'm not tolerating too much value between this ratio, right? So and so if epsilon is smaller, which means I have a stringent privacy requirement, then even if the sensitivity is fixed, if I need more privacy, then I need to add more noise. If epsilon becomes smaller, the noise has to increase. Similarly, if epsilon is fixed for two different functions that I want to compute, if one is more sensitive than the other, then I have to add more noise to the more sensitive function, because only then I will be able to confuse you between f of x and f of x prime, right? So that's why, that's the intuitive explanation as to why you need both sensitivity and epsilon as part of your noise statistics. Okay, good. So now all this is fine, but all that we have said so far is that, you know, if I compute f of x and add Laplace noise, then it's epsilon differentially private. Now I want to ask, how good is this, right? So I'm adding some noise, and that I know that the noise should depend on delta, the noise which is the sensitivity should depend on the privacy requirement, all that is fine. But I want to know how good is the final output that I'm telling you is the average. Let's say average is what I want, I care about, right? So I give you the average, and you know for sure it's not the average because I've added noise to the actual average and given you. But how much are you missing, right? So in other words, you should ask the same question as we asked for randomized response, which is the utility question. Because if you don't care about utility, then you can just give a random value, right? So, and we don't want that. We still want our mechanisms to be useful, because though we will not give you the exact average, I will give you a rough idea of the average, right? So, which means that utility is another important aspect. So, which means that we ask the question, what is the chance that, you know, at least the average case, let us say, where we know the sensitivity etc. exactly, minus what am I actually outputting? Well, I won't output this. I am actually outputting, I will first compute this, the curator will compute the exact average and then add a noise, right. So, this is what I am adding, right. So, and I am asking what is the chance? Well, you know, this is bad, right. So, in other words, what is the chance that or rather, so this is greater than or equal to, let us say, epsilon. In other words, this is the actual released value, basically f of x plus eta, that is what this is. This is the truth. And then I am asking how much am I deviating from the truth, right. So, basically that is what I am asking. And this is basically, I mean, you can already see that these two terms would cancel out, and it is just a function of the statistics of the noise itself that I am adding, right. So, and we can argue that this is going to be order of 1 by epsilon n. What does that mean? That means that my deviation is going to be controlled still by how much privacy I want and how much utility I want, right. So, just compare this with randomized response, right, RR, randomized response, where we said that, you know, with high probability the deviation from, you know, what you actually end up computing using the randomized response mechanism after doing the debiasing and so on, your estimate for the average versus the actual average, that was something like, if you remember, was 1 by epsilon square root of n, right. So, now this is an important distinction here, that if I want to achieve, you know, so let me actually say I mean, put both of these in the same terms, right. So, let me not even say this as probability, and I will just say that with high probability the deviation from truth is something like order of 1 by epsilon n, right. So, this is Laplace. Now, we ask the question, which is better, right. So, one thing that seems to be true here is that, you know, if epsilon is small, the more the privacy that you need, both of these are telling me that, you know, the utility will go down, right. So, smaller the epsilon, worse is going to be the utility, and that is very clear here, because, you know, smaller the epsilon, the larger the noise that I am going to add, which means that, you know, what I will see is a very noisy version of the truth. So, smaller the epsilon, larger the noise to f of x, or the average that I am adding, and so the utility goes down. That is clear. But now the question is, should I do randomized response or Laplace mechanism, right? So, how do we compare these two things, right? So, in terms of the privacy guarantee, both of these are epsilon differentially private, right? So, both these mechanisms, that is, everybody corrupts their input by flipping a coin and then gives the curator, and the curator does a debiasing and computes the average, gives it to the world. that is the randomized response mechanism, that is also epsilon differentially private. Or you trust the curator, give your correct value, curator computes the correct average noisy and releases a noisy version of it, which is the Laplace mechanism. That is also epsilon differentially private. Both are achieve the same privacy guarantee. Now the question is, if I fix an utility, right? So if I am saying that the chance that I don't deviate from the truth is bounded by some quantity, which is, let's say, a fixed value that I give you, then you can ask, how many points do I need, or how many people should I survey in the randomized response method versus the Laplace mechanism to achieve the same level of privacy utility trade-off. And that is where, this is a better mechanism, because the number here, the dependence on n is square root of n in the randomized response mechanism, whereas it is n in the Laplace mechanism, which means that, if I have a fixed amount of people, let's say 100 people, right? So then this is telling me that the utility is inversely proportional to the number of people that I survey. In both these cases, it's inversely proportional, right? So, but what is the way in which it is inversely proportional is important, right? So now this is telling me if n is 100, then this is by 1 by 100 epsilon, right? So which means that value is going to be much smaller than 1 by square root of 100 epsilon, which is just 1 by 10 epsilon, right? So which means that quadratically we have better utility in the Laplace mechanism than the randomized response mechanism. That's the difference, right? So in terms of privacy, both of these are epsilon differentially private. But if you fix a specific amount of utility that you would want to achieve and then ask, well, how many people should I survey? Then if you trust the curator, then you would have to survey quadratically lesser number of people to achieve the same privacy utility trade-off using the Laplace mechanism than not trusting the curator, in which case you would have to survey quadratically more number of people to achieve the same epsilon privacy trade-off. So because the model has changed, because I am trusting the curator, not everybody is adding noise, nobody is adding noise, I am trusting the curator, and the curator is adding a noise at the end after computing the average, and so you can you can kind of get away with adding lesser amount of noise in one shot than everybody adding their noise and the curator accumulating this, right? So so that's why, so this is a better mechanism than the randomized response mechanism. So so basically, so far what we have seen is, we have seen the notion of differential privacy, and we have seen a technique to achieve this, which is the Laplace mechanism, and that achieves a certain amount of utility. Now next time we will see a slightly different mechanism. Again, we won't have enough time to dwell deeper into these mechanisms because because of the limited time that we have in this course, but the goal of this course is also to give you an overview of what these mechanisms are and what kind of properties they have, as opposed to doing a full-fledged mathematical treatment of the subject itself, right? So which will take its own course. Nevertheless, next time what we will see is a slightly different mechanism, which is also going to achieve differential privacy, but not exactly, but in an approximate fashion, and we will talk about what does it mean to say approximate differential privacy, and we will see what is the utility guarantee of such a mechanism, and that we will see next time. So for now we have seen epsilon differential privacy and why the Laplace mechanism is a better way in the trusted curator model than the randomized response mechanism, which we saw last time. Next time we will see approximate notions of differential privacy. Thank you.